say impossible.
Right, because there's only so many probabilities.
Theoretically, you have two different messages that compute to the same hash. That is possible. You can show that mathematically.
Now try and do that.
That's a whole different thing entirely.
Right.
And therefore, it's also infeasible to get two originals with the same hash. It is theoretically possible, but not likely at this point. Now, infeasible means, first of all, we're talking about current technology and reasonably forecast. So if you take a look at hashing algorithms and things like that, and this is all related as well to encryption and similar technologies, what you will generally find is this particular standard has been estimated to be secure until the year 2030, based on where we think technology is going. NIST is the one who generally makes those kinds of statements.
Okay. IST?
NIST, National Institute of Standards and Technology. So, basically, what we're saying, when we say infeasible, we're saying we can mathematically analyze the level of resources necessary to crack all of this stuff. And say, yeah, ain't gonna happen. But it is an arms race. NSA, GCHQ, and criminals, it can be hard to tell the difference, are all eager to break encryption.
What do you say GCHQ is?
That's Britain.
Oh. All right, Britain.
General Communications Headquarters, I think is what that stands for, but it's the British equivalent of NSA. Researchers are always researching, and that's why I subscribe to a bunch of security blogs and keep up with the current state of the industry here. One of the things you may hear, quantum computing. Okay. Oh, that's going to change everything. With a quantum computer, they can crack any password in 37 seconds. All right.
Provided they can write the software.
Yeah. So
we're talking about an infinitely fast computer chip.
Well, the idea of quantum computing is it's like infinitely fast, but really what it is instead of zeros and ones, a quantum bit, a qubit, exists in a number of states simultaneously and can use all of those states in simultaneous calculations. So yes, it does speed things up immensely. Now, hashing algorithms. First one in major use, MD5, created by Ron Rivest. That's the R in RSA. Remember, RSA is Rivest, Shamir, Edelman, the three people who created it. MD5 created in '91, no longer secure. This is one of those things that happens with algorithms, is they work for a while, and then the technology catches up, and it's like, okay, we figured out how to crack this stuff.
And they're still providing MD5 keys along with ISO downloads.
And that's fine, because we're not trying to provide security. What we're trying to do...
Verify.
We're just trying to verify. Remember the thing with a hashing algorithm, if you change one bit in the original file, you will get a completely different hash. And so that's all we're trying to do, is say, there has not been a single bit changed in the file. We're verifying the authenticity of the file. We're not trying to secure things against attack. So MD5 with ISOs is fine. That's perfectly valid use. Next one was the secure hashing algorithm number 1, or SHA-1, created by NSA, and it was required for a long time in many government applications. But by around 2005, they were starting to find weaknesses in it. So that led to SHA-2. And SHA-2 is probably the best you're going to find right now. There was a competition that ended early in 2014 to create SHA-3. Bruce Schneier was one of the competitors. It turns out his algorithm was not the one chosen, but he was very good about it and wrote a post saying, well, it was a fair competition and, you know, the one they picked was perfectly good. But because it's very new, it's not in widespread use. So you're not going to find SHA-3. You hope you're going to find SHA-2. Now, we're talking about the version of the algorithm when we say SHA-1 or SHA-2. You might see things like SHA-256. And what that means is not the version of the algorithm, it's the bit length of the key.
Isn't SHA-1 128 and 2 256 though, or?
SHA-2, there's a number. The 256 is common, but you can have more. You can have 512. So, responsible owner, if you are taking passwords and storing them in a database, use encryption, definitely not MD5. Hopefully not SHA-1 anymore. Ideally SHA-2. Now, SHA-1 has been used for a while now in SSL certificates.
Not anymore.
Well, they're scheduled for end of life. Google is pushing to do it right away. Microsoft said we're going to remove support for it in 2017.
I think Chrome already does mark them.
What they're doing at this point is if you have a certificate that is authenticated with a SHA-1 key that extends into 2017, or is it into 2016? I don't remember now which one it was. But what it will do is it'll throw up a message saying, you know, we cannot guarantee that this site is secure.
Right.
So to warn you when to go there. You can still go there.
Right.
It'll just give you a warning. Google's gotten a certain amount of criticism for being a little too eager on that. Everyone in the industry thought Microsoft had it about right.
Wow.
Well, you know, the whole thing about certs, if you want, you know, I can do a presentation on SSL certs at some point. That's an interesting topic in itself.
Well, I'd like to see that.
Yeah. But basically, they're expensive. You know, it's like $1,000 for 2 years. So, now, in practice, your password, generally speaking, is transmitted to the site in the clear, which means you are vulnerable to a man-in-the-middle attack, unless you've connected via SSL. Now, browsers are starting to be configured to make SSL the default. EFF created a plugin. This is available for, I think, all of the major browsers that basically forces you to request an SSL connection. It's up to the site whether or not they honor that. Now, my site, which I showed you earlier, is wilnick.com. I don't have an SSL certificate. I'm not doing e-commerce. I'm just putting up articles.
They want to be public, so.
Well, you know, it's not that I'm opposed to it in principle. It's just I don't have $1,000 to spend to throw a cert up for no good reason, and then have to do it again in 2 years.
Certs are 1,000.
Well, okay. Do we have any other Ubuntu users here? Okay. Where did Mark Shuttleworth get all his money? Selling SSL certificates. A company called FAWT, T-H-A-W-T-E. He founded it, sold it for a pile of money to VeriSign. So, the money behind Ubuntu came from selling SSL certs. It is very lucrative.
I know we purchased a global cert for a couple of years, and it seems like it was like $500 for a global.
Sounds like actually
Wild
very,
card, I should say.
very interesting topic, and I'd like to take you up on your offer to do
Okay.
a presentation at some time.
Sure. Now, hashing is generally done on the site, and the hash is what is stored. And then on later logins, when you go there, you enter your password, they hash the password using the same algorithm, compare it to what's in the database. If they match, you're in. Done properly, that should be perfectly secure. Now, properly implies several things, that you're using a secure hashing algorithm, that the password has the right characteristics, blah, blah, blah. But this is, as Bruce Schneier says, trust the math. Now, dictionary attacks. This is how most attacks are done. A large number of passwords are created and the hash created. You know, hashing algorithms are public information. There's nothing secret about hashing algorithms. We've talked about them. They are standards. So anyone can use them. So what you do is you spend a little bit of time on a computer and you create a database of hashed passwords. So that's your dictionary, and then when you get to a site and you get a hold of their database and you copy that down, then you can do it just to compare between your dictionary database and the one you got from their site. Now, we have found through experience at least 50% of the passwords in any downloaded database can be found fairly quickly just by doing this dictionary attack.
Without any modification at all?
Right.
So there's a real common word that people use, password, for example. A lot of people are using that, so it hashes to a certain set of bytes.
Right.
See, most sites now won't take just letters, so...
Yeah, right.
And because this sort of thing happens.
Well, I'm sure things like password 01 is
Well,
also
actually, capital PASSWORD 1 is probably the most common for Microsoft servers.
Uh-huh. So, a lot of people use known poor passwords, and here there are lists of these things put out periodically. Here are some of the most common. These are like in your top 20 list of passwords. Now, for a while, leet speak, you know, that's where you substitute a number for a letter, so a 3 instead of an E, a 0 instead of an O, that sort of thing. That's all part of the dictionary now. So they've long ago figured that out. And since many people will use the same bad password, in that database, when we said 50% of them, you know, fail all at once, a lot of them are everyone using password as their password. You know, you get a whole bunch of those. So a solution to that is something called a salted hash. And that is a random number is added to the password before it is hashed. And that's called the salt. Now, understanding how this works, Brian has created a password on my site, and I assign him the random number 161803. Which actually isn't a random number, it's
I'm
the
glad I
golden
don't need
ratio.
to know the salt.
But what I have to do is I have to store in the dictionary, store in my database something that says, well, this is Brian, and this is his salt. I have to store that number, and then here's the resulting hash. So if someone gets the database, they get the salt. So why does this work? Because the cracker doesn't know what your password is. So they would have to recompile their entire dictionary with that one number, just to see if they can get your password. And then they have to repeat that again for every other password in there. So what it is it becomes computationally infeasible. Because remember, these people are not generally looking to just score one password, they're looking to score 1,000,000. All right? So salted hash will in fact defeat that, because it takes a certain amount of computing time to build that database, that dictionary that they're going to use.
How do they know the specific salt applies to a specific individual?
It has to be in the database.
Okay, so there's something in a database, but there has to be
Username.
Yeah.
Okay, so there has to be something that says this username uses this salt.
Yes.
Right.
Okay, so if they get that information also, then it defeats the salt.
No,
No.
because now they gotta do the dictionary for the attack with the salt in it, per user.
Remember, the hash has two components to it now. There
Alright,
is the
okay.
password and then the salt.
I mean, unless
Knowing the salt is interesting, but we don't know what the password is. And so that dictionary attack, where we get this huge dictionary of pre-computed hashes, we have to do a whole new version of that dictionary of pre-computed hashes using just this one salt.
Okay,
So
but there
unless-
would be, okay, so let me just jump one step further. So there are passwords, like password, which
Right.
are common enough that if they did that once for a whole long list of numbers, all the numbers from 0 to 90,000, right?
salt
Okay.
doesn't have to be numeric.
Then they would, well, yeah. Binary. Everything is numeric. Zeros and ones. So,
Right. Okay, so I'm just saying it is. You're right. It's computationally
right.
difficult, but if you still are using a bad password,
So-
it's still less secure.
So let's say it takes you a day to compile a dictionary. I could compile a dictionary using this one salt and maybe get Brian's password for a day's work.
Right.
Now, the next person in the database, I've got a completely different salt. I've now got to spend a day recompiling that dictionary and maybe get that person's password.
Well, I understand that concept. If
Right.
Brian is a real good Brian, and Brian does a password that has a number of characteristics that would make it unlikely other people are using that same password.
Right.
But if there is a bad Brian out there in this,
Right.
And
My
this
web
bad Brian
password
just
The
That's
other
bad,
people,
Brian.
if he was using password as his password,
yes, then he and all the people who
then
use that
the
bad
resulting hash is password plus his salt. The other person who used password has a different salt.
Yes, I understand it. So the one computation it takes to take that one number with the word password would be one of 90,000 likely numbers or
Right.
combinations. But then that one day they spend doing all those hashes, right, gets them most of the users that are using the password as
No,
password.
you're not getting what I'm saying. It might take a day to do a table of all of the possible passwords with just that one salt.
Yes.
So you're not going to get 90,000 different ones in one day. It's going to take you 90,000 days.
Okay, so I might have this flipped around. So
Yeah.
if you have the word password as your password,
Right.
and you run it against all the known salts you can come up with, 90,000 of them, and it takes you a full day to do that, right?
Oh, I see what you're saying.
So every single person who has
Then-
any salt in that table,
Okay, a password that bad, yeah, you might be able to do that.
so it's still, use a good password is still a worthwhile thing to do.
Oh, yeah.
Yeah.
Yeah, I'm not saying it isn't.
But this doesn't solve the problem of the people who are using really poor passwords necessarily.
You can't solve all problems. Understand the salt has to be stored because otherwise we wouldn't know how to let you in the next time.
Right. Well, you understand that there's got to be somebody out there, some cracker groups or whatever, that are going against all the known salts they can come up with all the common passwords. So they're no
Yeah.
longer have to do this one-day computation. That's probably already been done.
Now, if you want to see, here's a place that explains salting hashes and how to do that, if you're interested. So, that was the site owners. So, Gib, if I were doing this for your library patrons and we said, you know, there should be a break, this is about the point where I would say we take a 5-minute break. Because I'm now about to get into
Okay, well, let's do that. Let's
What
take a
happens to you
5-minute
with-
break.